All right, let's get started. We had left the last lecture just before we started talking about stack and procedure calls. So that's where I want to start today. Talk about procedure calls, and procedure calls are something that you guys have coded in C, Java, C++, whatever high-level language that you have learned, Python. You might have written procedure calls, right? So everybody has, right? A subroutine to do a particular task. So why is that useful? Why do you guys write subroutines or procedures or functions, whatever you guys want to call that? You write a main function and then you write a function to do this particular subtask. Go ahead. Easy to easily repeated. Okay, so if I have a certain set of instructions that are getting repeated or needs to be executed multiple times, then I can bundle all those instructions into one function and I can keep calling that function how many ever times I want. Some other motivation for writing subroutines? Go ahead. Right. So one was in terms of usability. The other was in terms of understanding. Right. So if you're trying to have just a general understanding for the user, you don't want to write like a 1,000 line code. You want to make it modular so that there is a level of abstraction, which makes for easily understanding the things. And if you're able to easily understand things, you will also be able to troubleshoot them, right? So if your task has a specific issue which is related to some subtask, then you know where to look for, right? So it makes things modular, easily understood by the reader, or it's easy for troubleshooting. And probably the sort of the most important one, as far as usability is concerned, is the fact that you will be able to reuse it many, many times. Abstraction, yes. Abstraction is the reason that was mentioned in the classroom as well. Yes. So those are the reasons, right? Now, where are you making all these procedure calls? In your high-level code. But how are they getting implemented? Well, somebody would have to convert that high-level code into MIPS assembly language. A compiler does that. So how does a procedure call that you write in C look like in the MIPS world? In the MIPS assembly language so far, we have been talking about do this add, do this RI, do this branch, do this load. We have not talked about function calls. So let's take a look, procedure calls. How are you going to write assembly for procedure calls? And whenever you are writing a procedure call, you will run into problem. And let's discuss that problem first. Is it fair to say that if I'm writing procedure calls, that is the first indication that I have a very complicated program that I'm trying to write up? Can I say that? If it was simple, then I would just write one main program with 10 lines of code and I'm done, right? If that was simple, it would be the case. But because it is complicated and has several modules that you're trying to use multiple times, that is the reason you would go for procedure calls, right? The task at hand is complex. And if a task at hand is complex, do you think that 32-bit registers would be sufficient? You will run short, right? You are going to have that limitation. On top of that, if you think about the registers that you can actually use for all these instructions, 0 register is reserved. You can't change that. There's a register reserved for assembler. There is a register reserved for stack pointer. There is a register reserved for return address. So among the 32 registers, there is already some of the registers that have a specific role and they have been taken away from us. The only registers that we have that we can actually use are the 8 saved registers and the 10 temporary registers, right? So out of those 18 registers, it is very possible that you will run out. So what are you going to do? Well, we are going to use the stack. to spill over the registers. So if you want to use more registers than you have available, then what you do is this. You save a register in memory, and the place where we save it, we are going to call that the stack. So we are going to place the register contents on top of the stack. We are going to use that register for whatever purpose we want. And after we are done with our purpose, we are going to restore the contents of that register so that at the end, it is the way it was before we started, right? You guys see that? So store, use, restore. Where are you storing? In the memory. So let's give it a specific name. In the memory, we are going to call that a stack. So wherever you need more registers than you have available, you spill over to the stack. That's sort of the main motivation for us to talk about stack. So let's talk about the example here. We have a subroutine or procedure. The name of the procedure is f. It is a function to which we need to pass two arguments, right? There are two arguments here, x and y. We are going to pass these two arguments using the 2 out of the 4 argument registers we have available, A0, A1, A2, A3. We are going to use 2 of them to pass the arguments to this particular procedure called f. And whatever it returns, it is going to return in the z variable, which is going to be some other register, right? So that's going to be the return value. And what are we using for the return values? We have 2 of them, V0 and V1, right? So we have 4 registers to pass arguments, defined purpose, and we have 2 registers that are used for storing the return value of functions. Purpose is defined. Now, place parameters x and y in the known place. What is that known place? Traditionally, we are calling that a stack. Do you have to do that? Not necessarily. We are talking about where all of this could go, right? X and y could go on top of the stack. If you don't need to do that, then we don't need to do that. So let's talk about that. When would you need to do it and when it is not necessary to do it? The only time you need to do it is if there is possible corruption of the contents of a register, right? Only then you need to worry about putting it on top of the stack and then later on removing it from top of the stack. But if there is no corruption that is going on for the contents of a register, then you don't have to place it onto the stack. Remember, where is the stack? In the memory, right? And we know that memory accesses are slow, right? So you are cringing when you are using a stack. You're cringing because you are making things slow. You want to be in the register file. Space is not enough, so I cringe and start using the memory. All right. So how are things going to go on when there is a procedure call? First, we are going to place the parameters x and y in the known place. When necessary, transfer the control through the procedure f. So from the main function, wherever you saw this instruction, f of x of y, whenever you execute that instruction, you are essentially passing control to that specific program. After that, you acquire storage resources needed by f. Typically, these are temp registers, T0 through T9, temp registers. And then we are going to perform the task, whatever that subroutine is, addition, multiplication, whatever that would be. We are going to store the result in Z and side effects. Essentially, that means that the temporary, well, let's talk about the side effects in 2 different categories. One is side effects could mean temporary registers that have changed value because of the execution of the procedure call. The other side effect is, how many temporary registers do you have? 10. What if you run out of those 10? What are you going to use? Well, you will have to rely on the saved registers. But saved registers were primarily meant for the main function. And then the temporary registers were used for all the subroutines. But if I run out of temporary registers, I'm going to use the saved registers, S0 through S7. But before I use them, think of them as property of the main function, right? Before I use them, what do I have to do? Store, use, restore. So that is also something that goes into the side effects category here. All right, let's place the result Z in the known place. Stack, or if you have a V0 register available or V1 register available, just put it in there and that is it. And then the last thing that you do is return control to the calling program. In whichever program you saw the instruction f of x comma y. Now, when we look at some examples with MIPS instructions to do these things will be a lot more clear than what they may be right now. So let's continue here. Procedure calls. Again, vast majority of procedure calls involve small number of parameters and results. So this procedure call has certain parameters and some return results, 1 or 2 returns, and so on, right? Small number of parameters that you're passing through to it and getting from it. What are we going to do? We are going to try to use registers in our register file as much as possible, and only when we need to spill over, we will spill over to a stack. Stack is nothing but a data structure in memory. That's all it is, which is being used for the spillover of registers. Remember, you want to be here, right? You want to use the registers as much as possible for speed. You don't want to be using the stack. So you avoid it as much as possible. The MIPS convention, what is that? Use registers for small procedure calls. So you have a function, main function, you have written an instruction that is for a procedure call. In the main function, I'm going to use saved registers. In the subroutine, I'm going to use the temp registers. If I just use saved registers for main function, if I just use temp registers for subroutines or procedures, I don't have to put anything on top of a stack. I don't have to use the stack at all. Saved for the main function, temp for the others. I'm done. The only time that I need to use the stack is if I need to spill over. Remember, this is also possible, right? You can have one main function and you can have one procedure within it, or you can have procedure 1, inside that procedure 2, inside that procedure 3. You can have nested functions as well. So if you have nested functions, then your chances of running out of the temp registers is also going to increase. So even if you are using temp registers, you may have to put some onto the stack if you need more than 10 temp registers. Next, allow access parameters to spill over to the stack. We talked about that. And we'll see this, and we'll see how we are doing it, right? So we need to understand a few things here. One, in C, what do you write? You write f of x comma y, right? You just write the function. You just call the function, sorry, in C. How are you going to do it in MIPS? You are going to do jump and link instruction. So there is the instruction used to jump to a specific location in the memory and start executing instructions over there. But it cannot be a simple jump. It has to be a jump and link. Why link? Because we are going to need to know where to come back after we get done with the procedure, right? So you are executing instructions here. You find a jump and link instruction. You go to your new space in the memory, execute the procedure call, and you need to know where to come back. So there has to be some linking. And there is a specific register which we are going to use to store that return address. RA register, $RA, return address. So whenever you are making that procedure call, you do that procedure call in MIPS by executing a jump and link instruction. So that's one. The other is, how are you putting data on top of a stack and taking it out? We are going to use the stack pointer for that. And we are simply going to grow the stack, put more and more things on top of a stack. And then as you use them, you remove things. So you essentially adjust your stack pointer. So if you guys have worked with stacks, you probably have some awareness of this, good awareness of this. But if you are new to stack, it is simply a piece of memory, right? Section of memory that we are using for this purpose, and we are calling that a stack. What is deleting something in a stack? There is nothing deleted from a stack. All you do is you move the stack pointer to the next address, next location. So when we say remove things from a stack, it is not like we are erasing something in memory. We are essentially adjusting the stack pointer, right? That's it. And we try to point always to the top of the stack. What are we using for that pointer? Stack pointer register. Register number 29, SP. That is used only for one purpose, to point to the top of the stack. All right, it will become easier if it is a little bit confusing here, it will get easier. All right, register allocation. What are the registers? Different type of registers we are going to use apart from the saved and the temporary ones. A0 to A3 for arguments. These are the registers we are using to pass arguments to those procedures. V0 and V1 for return values. RA for return address register. To understand the return of point of origin. Let's go. Like I said, a procedure call in C, such as calling the function, it looks like a jump and link instruction in MIPS. And what are you doing here? Jump and link. That's exactly what you're doing. Jumping to a new place in memory while you link your return address register with the next instruction. And there is a nice diagram on the next slide, which will give you guys some clarity. All right, jump and link, JAL. This is a J-type instruction, which means that there are only two fields here, opcode and then followed by a 26-bit address. When you have a 26-bit address, again, you do the same thing. You make it into a 26-bit, 28-bit address by adding 2 zeros to the least significant bits, right? Multiply by 4. And then you take the 4 most significant bits of the program counter and append it in the front of it. That's how you get your 32-bit jump address. JAL. This is what jumps to the procedure, right? So if you have written a procedure, what is a procedure? A procedure is, hold on. Better? Kind of. All right. A procedure is a set of instructions, right? In C, you just write a set of instructions. How does it look like in our MIPS ISA? It simply looks like I have a bunch of instructions. I have a bunch of instructions that are written in the memory, and I'm interested in the first address of that particular segment in the memory, right? Once I point to that, once I update my program counter with the first instruction where my procedure is, execute next, execute next, execute next. At the end, what am I going to do? I have that return address, right? So I'm just going to use another jump instruction, JR, jump register RA, right? So jump and link, come to the procedure, execute the procedure, and then the last instruction in the procedure will be a jump register instruction so that I can use the return address register to go back to my original function. Right, so that's your return address. We have talked about these things. Jump register, RA. So we have talked about 3 different types of jump registers, jump instructions now, right? Jump, no conditions, just jump to this address. Jump and link, used for procedure calls. Jump register, jumping to an address which is provided in a register. Questions so far? Easy peasy. All right, so procedure call and return. We are showing a block diagram in which we are representing memory, right? Not register file. This is just the memory. And what do you have? What all do you have in memory? You have data in your memory. You have programs in your memory. You have all the, all the procedures are also in the memory, right? P1, P2, P3, however you have, they're all in the memory. So suppose you are going through sort of a main function here. So suppose this is sort of a main function highlighted in blue. That's your main function. You're executing instructions in there. And then you encounter a jump and link instruction over here. JAL. After that, there is a X. What is that X? X is an identifier, a memory identifier, memory pointer here. It's going to have 26 bits. And then you can compute the 32-bit address from it. JAL followed by X. So what is that going to do? The moment you need to execute this, we are going to take the next address. What is that? PC plus 4, right? JAL is an instruction that we are executing. And if we are executing that, program counter is pointing to that, right? Which means the next address or next instruction is at the address PC plus 4. You guys okay with that? So what are we going to store in the return address? We are going to store the PC plus 4 in the return address, because when we are done with the procedure, we would not want to come back to PC. We would actually want to come back to PC plus 4 after the jump and link. You guys see that? Okay, so what happens there? When you actually jump, you are updating the program counter with this X. You have given that in the part of the instruction. While you are doing that, you are also linking, which means that you are saving program counter plus 4, the next instruction in your main function, in the return address register. And then you jump. Where are you jumping to? The first line in your procedure. You execute the procedure. What does that look like? It looks like using temp registers. Here is a question. I said S0 through S7. These registers are mainly for your main function, right? That's your primary function that is getting executed. And all the others, say temp registers, they are primarily used for the sub functions or procedures. An interesting question here is, can I use S0 for a procedure? So I have sort of isolated their functionality, right? You guys use saved, you guys use temp. That's sort of the default position. Why do we have a default position? So that we don't use stack for everything, right? That's why we have some assigned responsibility. Save for this, temp for this. But suppose you are doing some procedures, you are executing some procedures, and you're using temp. You ran out of temp registers because you had too many nested functions. Now you want to use saved registers. Can you use S0? There you go. So that means that when you're executing the temp registers, I don't have to put them on the stack in the procedure. But if I want to use saved registers, then I have to put them on stack, use the register, restore its value. You see that? So across the procedure call, saved registers need to be maintained. Temp registers can get corrupted. They can change across a procedure call. So hopefully that is clear. All right, let's keep going. First line of the procedure, this is the complete procedure. And the last instruction over here is going to be jump register. Where are you going to jump? I've given you an address in the return address, right? I've linked it. So go in, take a look at that register. You're going to find that address, jump to that address. So you go back to this guy, the old PC plus 4. Now here is a scenario. How are you going to handle this? Suppose you have some main function here, and then you have, say, P1 over here, some procedure 1. Then you have, say, P2 over here. How are you going to handle that? You have a procedure within the procedure, right? So from main, how many return addresses are you going to have here? So when you jump from main to P1, you use RA, right? Return address register. What are you using that return address register for? You're using it for when P1 gets done, where to come back to, right? That's what you're using RA for. Okay, so that's good. But during P2, P1, you're jumping to P2. What are you going to do then? What do you do with RA? Yes, put RA in stack, change it, so jump and link, go to the P2, execute P2, and when you are, after you jump back, restore, right? So you see what is happening. You have to be constantly be worrying about, I have limited number of registers. So if I have to use them multiple times, then I need to use the stack appropriately, right? Return address register, I have only one of them. So how am I going to deal with multiple sub-functions? This way, using the stack. So how does this work? You start with main, you execute the, you start getting to the main function. The control is with main. You are using mainly your S0 through S7 registers. And then you have a jump and link instruction, right? Which essentially maps to P1. How does it look like in memory? It looks like this, right? You have some main here, and then you have some P1 over here, then you have P2 over there, P3 over there. So these are instructions in the memory. Main, you had a jump and link, it jumped to P1. P1, it had a jump and link, you jump to P2, and so on. So that's your memory view. Yeah. Yeah. That all right, let me explain that. Suppose you are in main, right? And you're executing main. If for some reason you have to put certain things on top of the stack, what is that could be? That could be P0, right? Because you know that temp registers are sort of a property of the procedures, right? So if I'm using temp registers in my main function, then I'm going to need to put it on top of the stack. So while I'm here, I'm going to put some registers on top of the stack over here, but the control is with main, right? Then I'm going to go to P1. P1 puts something on top of the stack. Then P2 puts things on top of the stack. So this is the storing aspect, storing. Then using aspect, I don't have to show. But how about restoring? Restoring happens exactly in the opposite direction. So P2, so the stack pointer gets adjusted there, then P1, then main. See that? Last in, first out. So this is sort of your stack view. Questions? Go ahead. Yes. So in total, there are 1, 2. There's a jump and link instruction for P1. There's a jump and link instruction for P2. So 2 jump and links. Yes. And I have only one array. I can use it for the first time from main to P1, but when I'm doing from P1 to P2, then I need to put it on top of the stack, use it, restore. Stack is also part of the memory. So, it could be somewhere in the memory. All right, let's move on. Further issues. You're going to have a situation, you could have a situation where you need more than the 4 argument registers and the two return registers. What are you going to do then? The same thing that you did whenever you were spilling registers. You are again going to use the stack if you need more registers than they are available. 4 of these and 2 of these. Solution could be again preserved on top of the stack, right? So you have a limited number of registers available. You can use them without the need of the stack, as long as you are careful as a programmer that they are not getting corrupted. Those registers are not getting corrupted, right? Sometimes it may not matter, sometimes it may matter. So it sort of depends on the programmer to handle that situation. All right, let's talk about the stack. And this can be confusing. It has been in the past, but it's really adjusting a pointer, going up and down. That's all it is. So what is a stack? Like I said, it's a data structure for spilling our MIPS registers. It's in a last in, first out queue, like we just talked about. Last in, first out. Meaning if P2 puts things last, those will come out first, right? MIPS reserves the register number 29 for the stack pointer, which essentially points to the top of the stack. SP is a 32-bit register that points to the top of the stack. Everybody is expert at pointers, right? Everybody loves pointers. You guys have done C programming, yeah? Yeah. I learned C in 2001. I loved pointers. Still have nightmares about it. But that was 2001. Now the level of programming has dramatically changed. Anyway, so our stack pointer register is going to be pointing to the top of the stack. How is the stack growing? It is growing from higher to lower addresses. Now this can be a bit misleading, higher to lower addresses. So let me take a new slide here and talk about what squared paper after, sure. So let's take 2 boxes, 1 and 2. Say you have a high address here and a low address there, right? So essentially this is on the left, you have a memory view in which addresses are increasing as you go down, right? This is something similar to what we may be used to, right? Start with a small address, and then as you go down, you keep increasing the number, right? The address is 1, 2, 3, increasing as you go down. Addresses are increasing. Or you could have the other way. You could have high here, low there, right? For an address. Doesn't matter. It's just a view of the memory. So when I say the stack is going to grow from higher to lower addresses, if it is over here, it is going this way, right? The stack is growing up there, if that is the view. But if this is the view, it is going this way, right? This is my sort of $SP, say, right? I'm using $SP to point to top of the stack. So that's a location. And then I grow this way or I grow this way. So by adjusting the SP moves there, SP moves there, SP moves there, and so on. So it could look differently when you look at low versus high, how it is laid out. All right. How do you put things on top of the stack, and how do you remove things from the stack? Why do you need to remove things from a stack? Why can't I just keep placing it? Restore it. When I restore it, I need to adjust the stack pointer because I only have one stack pointer, which needs to point to the top of the stack. So I need to adjust that top of the stack so that after I restore and sort of go out, I have some other procedure that is going to use that for. Right. So placing data into the stack or onto the stack. What does that correspond to? That corresponds to subtraction from the stack pointer. Why are you subtracting? Because you are going from high to low addresses, right? So if you're going from high to low addresses and you're adjusting, you're growing that stack, you are going, if you want to place data on top of the stack, you adjust the stack pointer first, subtract how much from it? How much am I going to subtract from SP so that I can push data, push one word on a stack, on the stack? 4, right? So SP equals SP minus 4. So I need to subtract 4. So subtract stack pointer 4, store the result back in the stack pointer. Then what can you do? You can do a store word. So subtract, store word, you have placed the data. Then you execute whatever you want. At the end, what do? Load word from that SP and then add 4. When you add 4, it is essentially like pop operation, which is to remove things from the stack. So subtract 4, use it, subtract 4, store word, right? Store word takes the content of a register that you want to use, puts it on top of the stack, and now you are free to use it the way you want. After you get done with using it, you have to restore. What does that restore step involve? Load word first, right? Load word from $SP, which is now pointing to the top of the stack, to this register that you used, followed by an addition operation. SP equals SP plus 4. So those are called push and pop operations. Pushing data on top of the stack, popping data from top of the stack. Questions here? So this is just a diagram to show that higher address, if it is here, your stack is growing up that way. And every time you're doing SP minus 4, SP minus 4, SP minus 4, store word, store word, store word. Questions? Example is necessary. We'll take a look at that. All right, so let's talk about sort of the classification that we have already talked about a few times, which is essentially the difference between the saved and the temp registers. What is preserved across a call and what is not preserved across a call, which in other words means what is still the way it was after the procedure call. So after the procedure call, the saved registers need to be the same. S0 through S7 cannot change, right? You are in main, you go execute a procedure, you come back, I expect S0 through S7 to not have changed, which means that if you want to use them in the procedure, you better put them on top of the stack. Similarly, for stack pointer and the return address, and whatever is above the stack above the stack pointer, all of that is going to be preserved across a procedure. That means that when you make a procedure call, however it was, however these 4 things were, whenever you return, they will be the same. What is not preserved across a call? The temp registers. Procedures can use temp registers. They change the contents of the temp registers. So the main function cannot expect them to be the same before and after the call. Similarly, for argument and the return variable registers and the stack below it, below the stack pointer, that is going to be not be preserved. It's going to change. Next, here is an example. So what do we have here? We have a example procedure, some procedure called example, which is written in a main function, right? There's a main function, and this is another example function that we are trying to execute, do a procedure call for. What are its arguments? There are 4 integer type arguments, G, H, I, and J. And there is some return value, only one return value here of integer type. right? That's your C program. What are you doing? You are initializing f as an integer data type. You're doing g plus h minus I plus j. That goes in f and return the value f, right? So you've got 4 arguments and one return value. All of this is written in C, and I'm assuming that this procedure is inside a main function, right? So this is a procedure. And let us suppose we have this particular assignment. For ij, gh, because these are arguments that I'm passing to the procedure, I'm going to use the 4 argument registers. Then I have a return value going into v0. I could have used v1 as well. But here is an interesting thing. The local variable that I'm using inside example is s0. Not the best choice, right? What would have been a better choice? Good. A temporary register would have been a better choice. Why? I don't need to put it on top of the stack. Then why are you using S0? Because I want to show you guys how to put things on top of the stack, right? So over here, S0 is being used to just demonstrate how to put things on top of the stack and how to remove them. But I hope you guys understand that a better choice would have been a temp register, because I wouldn't need to put it on top of the stack there. All right, let's actually get into the example here. So we have the same C program over here. We have a view of the stack on the right there. And then on the bottom here, we have all your MIPS instructions. So how are things going to work? Suppose there was a jump and link instruction in the main program. And that jump and link instruction pointed to example, the first line of where example procedure is written in memory, right? So in other words, I'm not writing the jump and link instruction over here. I'm assuming that that is in the main program. I'm writing instructions of just the procedure. Let me be a little bit more clear about this. I'm not writing this, right? I'm only writing this guy, right? I'm only writing the MIPS for this. I'm not writing the jump and link. In fact, I'm not even writing the jump register at the end. I'm just writing these guys. How do you write the procedure itself? Let's see. Which is why you don't see a jump and link. In fact, you also don't see a jump register at the very end. We are just seeing the procedure example here. So what do? The first thing that you do is immediate subtract immediate. Why are you doing this? You're doing this so that if your stack pointer is pointing to a high address here, you're going to move it up, which means subtract 4, right? So now the stack pointer is pointing to the address above it, to the word above it. You do that first, right? Subtract immediate, SP equals SP minus 4. Adjust the stack pointer first. Why are you doing that? I want to use S0 during example. So I want to save it first. How do you save it? You simply execute a store word instruction. Store word S0, offset is 0, base address is in SP, right? Whatever you have in register S0, put it at an address computed by SP plus 0, which is SP, which is what? Pointing right here. So what did we just do? We just put $S0 over there, right? Maybe I can do better here. The contents of $S0, I've put it there. So wherever I need it, I can do that. I can look into the memory. All right. So save register S0 is done. Then I can do this. I can do the addition here, subtraction there. Addition here. What is that for? Oh, hold up. This addition is for G plus H. This addition is for I plus J. And then there is a subtraction for this subtraction. Right, simple R-type instructions to do the addition, subtraction. Shouldn't be a big deal here. Let's see. A0, A1, A2, A3. Those are being used for the arguments that were passed. T0, T1 is being also used, but without the need for putting them on top of the stack, because it's a procedure here. So those are the only two things that I want to say. Next, I want the return value to be in V0. So I'm going to take the result, whatever I have, and put it in V0 by executing this add instruction. I'm done with my procedure. What do I need to do now? I just need to return the value f. How do I return? Before I return, what do I need to do? I need to restore the contents of S0, right? So where is my stack pointer pointing right now? Is right here, right? So when I do the load word into S0, it is going to load this guy, right? The right register. So I do a load word. What goes into what? Well, address computed by 0 plus stack pointer in memory goes into S0. That is effectively restoring the contents of S0, whatever it S0 was before you started executing those add and subtract instructions. After you do the load word, you're done with this. What do? You come down, add 4 to the stack pointer. So now again, it is pointing to the top of the stack. Whatever location in memory you had above it was used and was removed from the stack. So it's not like removing things from top of the stack doesn't mean making them 0 or deleting it. It just means adjusting the pointer. Questions about this example? Good. S0 has been restored. Because you see, every time it goes back to the same, this conversation. Right? If you are in main, you are here, 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 here. So the stack pointer needs to go here, right? And then when you're done with P2, then you need to sort of remove these things so that you go back. Right? So it's like Inception. You guys have seen the movie Inception, right? It's like that. Go ahead. What if there are 2 things? What if there are 4 things? You're going to keep adjusting the offset based on an estimate about how many things you are storing, right? SP is what? Top of the stack, right? When it is pointing to the top of the stack, it essentially means that whatever you have over there is right now valuable, is stored by somebody else. We don't. So here, when you are going from say P1 to P2, right? When you go into P2, there were things written by P1, right? That's where it is pointing right now. So I can't put it right. Oh, minus first. Right. minus 4, minus 4, minus 4. Yeah. So minus 4 store, minus 4 store, minus 4 store. If you are the programmer, you could do it, but it would not be a very efficient way of doing it. Like you would have to keep track of your operations and how many are you doing it. You would have to keep track of that. Instead, you just go systematic, right? Go up, put it there. Go up, put it there, and so on. I saw the hand here. No, no. It's just a piece of memory segment that is allocated for this purpose. Good. So when you're going 12, right, you have created a space for 3 words to come, right? So you can go there. Which instruction are you going to use at that time? So suppose you did 12, subtracted 12. You went up by 3 words. When you went up by 3 words, like we used store word instruction to place data over there, which instruction are you going to use to store word there? Are you still going to use store word? If you do, then it will only occupy 32 bits. What about the 8 what? 8 bytes below it? They are not being used, right? Yes. Yes. Yeah, that's okay. But the issue is this. When you do minus 12, you store a word there, and then again you have to adjust the stack pointer anyway. You have to do plus 4, or store plus 4. It's like, and then you are stuck in the middle. Now your stack pointer is pointing to something in the middle, and you don't know whether things above it need to be preserved, below it need to be. All right. Other questions? I think that was. So as far as stacks are concerned, this is what we are going to discuss. Again, a lot of people have suggested that our discussion about the stack is limited, and they asked me, did we talk about stacks? We did. Right. All right. Let's talk about the 5 addressing modes in MIPS. This is going to be pretty easy to follow. If you have been paying any attention in the last 2 or 3 classes, this is going to be a breeze. There are 5 addressing modes in MIPS. And it depends on how we are referring to an address or an operand. There are 5 of them. Let's go into each one of them and discuss details. First one is immediate addressing. Immediate addressing is an addressing mode in which the operand is provided as an immediate constant as part of the instruction. So where is the operand? Immediate operand is a constant that goes right here. What is it? It is a 16-bit signed constant. An example of immediate addressing can be seen in add I, subtract I, or I, and I. All of these arithmetic or logical operations with an I at the end. Those are all your immediate operations. Operand is a 16-bit constant. First addressing mode. Second addressing mode is for register addressing, R-type instructions. What are we doing here? We are referring to an operand as a register. Operand is a register. You have 2 operands over here. Well, two different registers over here, but three operands, two source operands and one destination operand. All the operands are being referred to by a register in MIPS, one of the 32 registers. Register addressing. Operand A is a register. Earlier, operand was an immediate addressing. Base addressing, load word and store word instructions. Different from branching instructions. Why? For load word and store word, your addressing is in terms of bytes. For branch instructions, your offset that you provide is in words, right? So slightly different there. This is for base addressing. And these are the only two instructions in which we have anything to do with the memory, bring things from memory or store things to memory, right? I hope you guys are all in agreement with me when we say that jump, load word and store word are the only two, those are the only two instructions that have things to do with the memory. Otherwise, we are in the register file. If you want to move things to and from the register file with the memory, then you need to use the LW or SW, load word or store word. So this is an I-type instruction, right? And in the I-type instruction, you have operand two sources followed by a 16-bit offset address. So what is your addressing scheme here? Base addressing, right? So you're providing the target address using two things. One, the base address is in the register. And then the offset address is a 16-bit signed constant, which is part of the instruction. So you take the base register, which is in a register, base address in a register, add it to the offset, right? And what do you get? You get a target address. With a target address, you can address any byte. It's a byte addressable scheme. It's a byte addressable ISA. So with the target address, you can point to any byte. A byte is in a half word, which is in a word, right? So over here, I don't want this diagram to be confusing. This is simply showing that this byte is half of the half word, and all of this is half of this word. But we are able to address a byte in that because it's a byte addressable ISA. So that's your base addressing mode. Operand is where? Operand is at a memory location. How do you find the location? Take the register, whatever it is, add it to the immediate constant, and you get your location. Whatever you have at that location in memory, that is your operand. For example, over here, T0, 100, T1. Base address in T1, add 100 to it, you get your target address. That's where you would store, that's where you would load things from to T0 register. PC relative addressing. This is for branch instructions, branch when equal and branch when not equal. This is also I-type instructions, which means you have a 16-bit immediate in the instruction. Also has 6-bit opcode, 5 bits for RS, 5 bits for RT, and then you have your address. What do you do over here? Well, you have address in terms of word. This is the offset provided in terms of words. You convert it into bytes by multiplying by 4. You add it to PC plus 4. Why are you adding it to PC plus 4 and not PC? Why not PC? Branch when equal or branch when not equal. Take the offset in words, right? Convert it into bytes. and then add it to PC plus 4. Question is, why not add it to PC, just PC? So here, two things can happen when the branch instruction is satisfied or not satisfied, right? If it is not satisfied, which is the instruction it is going to execute? PC plus 4, right? Because branch instruction is appearing at PC. The next one is PC plus 4. So if you don't branch, then you are executing PC plus 4. So if you branch, it should be PC plus 4 plus offset. You guys see that? All right. Add that, and that will allow you to access or branch to a word instruction which is located at that particular address. The address was computed by adding an offset provided in Word and PC plus 4. So right now, as you're seeing all of these things, I want you guys to start picturing the hardware for this. It looks like I need an adder, which is going to be used a lot, right? It looks like I'm going to need an adder that always adds 4. I'm going to need something that can do sort of a sign extension, right? Because suppose you have add I, right? Add I instruction. What are you trying to do? Add I. Add I instruction is register 32-bit address, 32-bit register contents plus 16-bit immediate. How are you going to add those up? Well, you'll have to do a sign extension. So I need to have a sign extender. So as you are learning about all these addressing schemes and the instruction set itself, I want you guys to start questioning, what would I need in terms of hardware to get this done? Because our 3 lectures down the line, we are going to actually look at that hardware and track our instructions from start to finish. And like I said, you're going to see a sign extender, you're going to see adders, you're going to see ALU, you're going to see register file, you're going to see a lot of muxes. All right. So next, let's talk about the alignment of programs. And I think we have done a pretty decent job talking about alignment. The difference between word aligned and byte addressable. So MIPS ISA supports byte addressable. So whenever I'm addressing something, I'm going to address them by byte addresses, right? So there are two things, generally two things that your memory will have: data and programs. When there is data, you could put data anywhere and any byte address because I can do a byte addressable scheme. However, when I'm writing programs, programs are going to be word aligned. Why? MIPS instructions are 32 bits, right? So 32-bit, word aligned programs. So MIPS is going to have word aligned programs, and it's also going to be byte addressable. And for word addresses, addresses must be divisible by 4, because you know that we have computed it by multiplying it by 4. 4 bytes, one word. All right, here is an example of the branch when not equal instruction. We have been talking about the range of numbers, range of that offset, right? So if you have 16 bits and you are providing that offset in words, then you are going to have a range of words that you can branch off to relative to PC, right? What is that range going to be? It's going to be 2 raised to 16, 2 raised to 15, plus or minus 2 raised to 15 words, which means it is going to be 2 raised to 17 bytes. That's going to be your branching away from program counter. So if your program counter is here, you can go plus or minus 2 raised to 15 words. If I wanted to be really specific, I would say on the minus direction, I can go 2 raised to 15. On the plus direction, I can go 2 raised to 15 minus 1. Most branches are local, which is sort of a principle here, which is principle of locality. Principle of locality is one of the key principles in computer architecture, which is essentially which essentially boils down to this. If you have memory accesses to memory, right? Like if you're trying to read memory, for example, programs tend to read memory locations that are closer to each other more often than I'll read here and then I'll read here and then I'll read here and then they try to read in clusters. So there is very high correlation in memory accesses in space and time. So there is temporal locality and there is also spatial locality. And when we go into memory, we'll talk a lot about that. But that's what this is useful for. Whenever you're branching off of program counter. So you're branching to things that are supporting that principle of locality. You're not branching very far off. What do you do for very far off jumps? You use the jump instruction. All right, let's get into this, guy. We are trying to execute this. Branch when not equal. This particular example that I have over here, I think a variation of this was asked on last semester's exam as a multiple choice. The average on that was about 50%, so not impressive, right? So that has stuck with me, that students did not get this concept really well. So all I did was I asked them what would be the branching address, where would it branch? And I just adjusted numbers here. So what is it? At some memory address location, the address is provided in decimal, right? So in decimal, you have 80016, and at that particular instruction, you have a branch when not equal instruction. What are you comparing it with what? T0 is being compared with S5. The contents of T0 and S5 are being compared. And if they are not equal, you jump or you branch to a memory location which is labeled, which we are referring to as exit. But a few things about exit. Exit is not an address, it is an offset address. That is being, the units are what? Words, right? So whatever you see in exit, you're going to need to go from words to bytes and then do that PC+4 addition to find out what that branch address is going to be, right? So remember, if hold on to this, let's go back. For branching instructions, our addressing mode has what? Address in bytes, address in words, PC+4, add it, get the address, right? That's where you would jump to. So the question is, if I were to write the 32-bit machine code for that instruction, what would I write? For B&E, you would get 5 from the opcode, right? Look up the MIPS reference sheet. For B&E, it will be 5. For T0, it will be 8. For S5, it will be 21. Those are the register numbers, followed by exit. Okay, I need to provide this in words. Where is exit? Exit looks like it corresponds to a memory location, which is 80028, right? So you've got 16. What is the next instruction there? What is this address? I shouldn't have drawn 3 boxes. Now you guys know the answer. Hold on, no. You only need 2, right? +4, right? So the instruction is at 16, next one is at 20, next one after that is 24, after that it is 28. So if PC is this, PC +4 is 80020, and you add what to it? Words times 4 to it, right? So if this guy was 2, the offset in words, right? Multiply by 4 to get it in bytes, you got 8 bytes. Add it to PC plus 4. PC plus 4 is this guy. Where should I? This is what? PC plus 4. I'm assuming this is PC. I'm right now executing the BNE instruction, right? So that's PC. The next instruction is PC plus 4. I add 2 times 4 to it. I get my exit. Actually, the label is exit, but where is it? It is at the address 80028 in decimal. The addresses are in decimal here. You guys see how that, so the question, I think I asked the question, I gave them something like this, a variation of this, and I simply asked them to compute this. It was either that or I gave them this and I asked them to find this. One of them. You guys see how to do that. Oh, it cannot be. It cannot be, right? So you as a programmer, you have to, and the compiler is doing that for you, right? Because you operate at the high level language level, C level. So the compiler takes care of all that. However, if you were trying to write it, then you have to make sure that your MIPS instructions are consistent with the memory, the way it is being used. So you cannot branch to a place where you have some other program, because that is going to corrupt it there. So that responsibility falls on the programmer or on the compiler. Compiler followed by assembler. They'll do that for you automatically. Questions? Easy peasy? All right. So tell me where most people make a mistake here. I said 50% success rate, right? What do you think the other 50% answered? Or which aspect of this they got confused by? Good. Actually, they did that correctly. They plus 4. Yeah, they didn't do the plus 4. All right. So they missed this. All right, let's see. Okay. Last type of addressing. This is pseudo direct. Meant for what? Meant for the biggest jumps that are possible with MIPS, right? That would correspond to what? 28 bytes. 28 bit for the byte addressable memory. What does a jump instruction have? By the way, this is what? Jump is 1. Jump and link is 1. And the other jump instruction that we saw, which in fact was an I-type instruction, is a jump register instruction, JR. So JR is an I-type instruction. These two are the J-type instructions, jump and link. So how does it go? You have opcode for jump. I think it is either 2 or 3 in hex, followed by a 26-bit word address. How do you compute the byte address for this? You go from 26-bit to a 28-bit word to a byte, multiply by 4, or shift left by 2 bits. And then you get the 4 most significant bits from the program counter. So essentially that means that when you are doing branching, right, this was the program counter, and you were able to do sort of, this was the range of you to branch. Now when you're doing jump, it's still relative to PC, but it is a huge jump away from PC, because then you had only 16 bits to provide the word offset. Now you have 26 bits to provide that word offset. You guys see that? Yeah? So bigger jumps with respect to PC. And your range is going to be 256 megabytes away from program counter. So really big jumps are possible with this. Okay. How are we doing on time? 9:15. We have got time. All right. This completes instruction set 1 and 2. Next, we get into arithmetic for computers. And when we talk about arithmetic for your computers, again, we are going to do this in sort of 2 parts. I'll kick things off with the first part today. And hopefully, you guys, if you guys have done multiplication and division in high school and you enjoyed that, you are going to enjoy this. So what we are going to try to figure out is, how is multiplication and division actually carried out in hardware? COCO gives you what? Computer components and operations gives you a lot of insight in addition, right? Adding, how do you represent numbers that are signed? It gets into the hardware as well, like carry, look ahead, adder. But it doesn't go into multiplication that much. I used to do it, but we talk about it more efficiently over here. So we'll get into multiplication. We'll review decimal multiplication as well. And then we'll look at binary multiplication. And the most important thing that we'll do is find very efficient hardware to perform multiplication. That will be my goal. Let's see if I can meet it. Again, this is going to be part 1, part 2. Part 1 will focus on multiplication, division, hardware. Part 2 will focus on the IEEE 754 standards. There are 2 of them. How do you represent 32-bit numbers and 64-bit floating point numbers in your computers in the IEEE standard, right? Meant for really, really small numbers to really, really large numbers. How do you express that in 32-bit IEEE format and 64-bit IEEE format? Conversions, essentially. I'll give you the 32-bit number. Can you tell me what its value is in decimal? I'll give you the value in decimal. Can you tell me the 32-bit sequence in that IEEE standard? So that will be sort of our next lecture. But today we'll start things off with multiplication. So in order to get there, we need to talk about signed numbers. And the first statement is sort of very evident, right? Bits do not have any inherent meaning. If I give you a bunch of zeros and ones, you are not going to know what that is for. Is it an instruction? Is it an integer? Is it a floating point number? Is it just arbitrary data? The bits do not have any inherent meaning. You are going to need to provide context and then bits, and then you know what those bits correspond to. Now, the complication because of that is, how do you represent signed numbers versus unsigned numbers? What do you do with overflow? Because you have finite number of bits. You guys know that for overflow is going to occur during arithmetic operations when there is a limitation on the number of bits, right? We have seen that in COCO. That's probably the first, second lecture of the semester there. You have a limitation on number of bits. When you add or subtract, you are going to overflow. In other words, you are going to get an incorrect result. And the other complication is, how do you represent fractions and real numbers using the same standard? There were 2 main signed representation schemes that we looked at earlier. This is what earlier meaning, last semester or last year, like COCO material. Signed magnitude representation, which we did not like that much. And then we moved into 2's complement representation. What was the reason why we didn't like signed magnitude? Anybody remember? Oh, that is nitpicking, man. That was all right. Smaller range. What is? Okay, so it's yes, it is smaller range by 1, and then because of the 0, right? So you have 2 sequences representing 0, which is why you lose 1 in the range. That is also a disadvantage. But the bigger problem is, when you start doing the arithmetic, you will need a lot more hardware to get the right answer. What was the hardware? Anybody remember? To get the right answer, you would need a comparator, right? No comparator necessary for addition and subtraction in 2's complement. In fact, you only need addition in 2's complement, because even the subtraction, you were able to accomplish subtraction by doing a pseudo addition, right? False addition. So need for comparator over here, that was the problem. Needs, because you need to find or determine the sign of the result, right? If you want to find the sign of the result during addition, subtraction of signed numbers, then you need a comparator so that you can adjust that sign. So that was the problem here. A lot more hardware required to get the right results. That's why we tended towards 2's complement, and that's what we are going to use. 2's complement addition sub arithmetic. All right, so everybody remember sign magnitude? Treat sign and the magnitude of the number separately. One bit for the sign, the other few bits, whatever remains, for the magnitude. Everybody loves this because 1, 1, 1. All right, 1, negative, 1, 1, 3, negative 3. Right? So it's pretty easy to do that conversion. But we have a problem there. For 2's complement, works really well with arithmetic, doesn't need a comparator, has one more bit for the range. Yeah. So it doesn't have 2 bit sequences for 0. It just has 1 for 0. Over here, we are still using the most significant bits for sign and the other 2 that are related to the magnitude, not magnitude, but related to the magnitude. All right, so let's just do some quick recap, see if you guys remember this or not. Let's pick this guy. Well, let's pick this guy. 100 in 2's complement form. If you are given 100 in 2's complement form and you are asked to find the value in decimal, you are going to first look at the first one and you are going to say, oh yeah, I see this one, so it's a negative number. And then you are going to find, you are going to need to find the value of the number. And the way you find the value of the number is take the number, flip all the bits, so it becomes what? 100 flips, flips, and flips. And then you add 1 to it, right? So what do you get? You get negative 0, 1, 1 plus 1. And then, of course, you are going to need to convert that. So negative 4, right? Everybody remembers this? Yeah? Okay. Negation and extension. Now, sign extension is something that we are going to need. We have established that already, right? Our immediate instructions, add I, and I, all of these immediate type instructions have constants that are signed. So if they are signed, that means that they can be positive, they can be negative. And if they can be positive or negative, and if you only have, say, 2 bits, and if you have to generate a 16-bit sequence for that, because it's a 16-bit field, you're going to need to do a sign extension. So you're either going to pad it with zeros on the most significant positions if the number was positive, or pad it with ones if the number was negative, right? So it is simply copying the sign of the number and extending the number to whatever bits you need. So for example, if you had something like this, 0010, and if you had to do a sign extension for one application, the application is make a 4-bit number into an 8-bit number, right? You are trying to convert 4 to 8-bit. In our conversation, this is going to more or less look like 16, make a 4-bit into a 16-bit, or 16-bit to a 32-bit, something like that, or 32-bit into a 64-bit, right? The size is going to increase. But what are you doing here? You're taking the sign, which is this guy, and extending it, right, to just make it 8-bit. Works for positive numbers as well as for negative numbers. So if you see this, the negative number, extend the sign. Very useful while doing multiplication. Why? Multiplication is repeated addition. Agreed? Next statement. While doing additions, I can get overflow. Agreed? Yeah? In order to avoid overflow, I need to do an extension. If I do sign extension of the result every time, because multiplication was add here, add here, add here, add here, add here. Every time you add, you could end up in an overflow situation, which means you could get a incorrect partial product. If you get incorrect partial product at one place, the whole answer is wrong then, right? So in order to avoid overflow, at each step you add, this is what you do during multiplication. You add, sign extend by 1 bit, add, sign extend by 1 bit. Because in order to avoid overflow, you only need to increase 1 bit. That's it. So every time you add, you sign extend by 1. So that's used to avoid overflow while addition is going on, which constitutes a multiplication operation. So that's sort of the need for sign extension. There are other things as well. For example, in MIPS, what is the need? Well, we have a 16-bit immediate. Our operations are for 32-bit, right? Whenever you do add I, 16-bit immediate added to 32-bit contents of a register. How are you going to do that? You need to extend the sign here, then add 32 and 32. Also, unsigned versus signed instructions. Some instructions are signed, add. Some instructions are unsigned. So forget about the sign. This bit is not used for sign. For example, add U. Or over here, the example is load byte and load byte unsigned. So you can have sort of variations of signed versus unsigned instructions as well. All right, overflow. How do you detect overflow? You guys were champions at this. How do you detect overflow? Positive plus positive, you get negative. Incorrect. Overflow. Negative plus negative equals positive. Incorrect. Overflow. You also can monitor that with respect to the carries, right? Carry in and out of the most significant into the sign position. You guys remember that? Carry into the sign position and out of the sign position. If they're different and the same, it signifies overflow or not overflow. So there are ways in hardware you could detect overflow. But the simplest way would be what? Well, incorrect result is overflow. Sometimes you may not care about overflow occurring. You might just choose to ignore it. I'm doing these arithmetic instructions, and whenever overflow happens, I just want you to ignore it. Or a better way to do this is detect overflow. And if you detect overflow, start executing an exceptional handler program, EPC. So an exception handler program is a procedure that is present in the memory, which has instructions that denote how you want to handle an overflow condition. What are you going to need for this? You are going to need an exception program counter for this. So this is a register that will store the address that points to the exceptional handle program. So what you do is your program counter will get updated with the contents of EPC, and then you jump to EPC. And wherever you interrupt it, you will also need to do a link for the return address. Another way of dealing with overflow is simply to ignore it. And you could have separate instructions for signed and unsigned addition, add U versus add. And because it is unsigned, overflow is treated differently compared to a signed arithmetic, such as add. All right, let's see here. Things are becoming a bit boring, huh? How many people are there in the class right now? Any idea, you guys? Where is my participants window? I can't even bring this up now. What? Oh, this guy. There you go. 12. Two of them are me. 10 people online with like 10 people over here. Okay, guys, we need to not do the same thing we did last semester. All right, last semester after March, say April. April was like burnout month. Everybody was talking about burnout. We took a break. We had final exams which were cancelled. We have a lot of positives that happened. I don't remind me of that same time. Or this class is probably too easy. That could be it. Class too easy, huh? All right, let's get into pipelining. And we'll talk about if this class is difficult or not. All right, so we are talking about overflow. How do you handle it? All right, these are the ways to handle it. Exception program counter. Okay. So a recap of multiplication. 4-bit example. Multiply 11 and 5. You get 55. Always. How do you represent that in binary? 11 in binary, 1011. I'm using unsigned multiplication here. For 5, I have 0101 in binary. For 55, I have 110111 in binary. First thing to note, my numbers were 4-bit each. However, my result was not necessarily 4 bits. It was more than that. In other words, whenever I'm using hardware to store multiplicand, multiplier, and the answer, which is in the product register, I'm going to need a bigger product register than the numbers itself. How bad can it be? Well, if you have 4 bits and 4 bits, your answer can go as much as 8 bits. So for example, if you had a 32-bit number, you are trying to multiply with a 32-bit number, your answer could be as big as a 64-bit number. So you need to have a space for 64 bits. Right? So 15, 15, 255, 225. By the way, is this the biggest one? That wouldn't be the biggest one, right? Because in decimal, you can go up to 99. 99 times 99, you multiply that, you will see the answer in decimal. It will be very close to all ones. But you will need 8 bits. That's the point. So how do you do it in binary? Some may have seen this, some may not have seen this. But before we talk about the hardware, we need to talk about the multiplication algorithm, because they are both going to be connected. You have two numbers over here. They're both 4 bits, 11 and 5, 1011 and 0101. Multiplication is commutative, so you can have multiplicand and multiplier switched. But right now we have 11 representing the multiplicand and 5 representing the multiplier. And they are 4 bits each, so that's, very nicely we have written one on top of the other. So how do you do multiplication? What do you look at first? Of all these numbers, what do you look at first? The top one is multiplicand and the bottom one is multiplier. Which bit are you observing first? Good. Multiplier, beautiful. The least significant of the bit of the multiplier is going to open up. That's like the key to unlock all the other steps, right? Because that's going to be your first step. The least significant bit of the multiplier could be a 0, could be a 1. What do you do when it's a 0? What do you do when it's a 1? Well, if it's a 1, you're simply going to put the multiplicand down here if it's a 1, right? Now think about it in terms of hardware. If it's a 1, what do you do in hardware? Imagine this. You have a product register which is, so imagine 32-bit register getting multiplied with 32-bit register. One register is for the multiplier, one register is for multiplicand. Your product register needs to be how many bits? 32, 32. 64, right? So our product register needs to be 64 bits. Let us initialize them with all zeros, okay? Before we begin multiplication, let's all assume that they're all zeros. Now, what do I need to do if my least significant bit is 1? What do I need to do with the product register? Multiplicand, right? So I just need to add multiplicand to the product register. That's all, right? So 64 zeros, I've got 32, whatever multiplicand is. Just need to add multiplicand to my product register, which was initialized appropriately. That's it, right? Good. Over here, I'm just doing unsigned multiplication. So I'm just looking at it in terms of multiplication operations right now. So if it's a 1, you do that addition. What if this was 0? What would you do to the product register? Nothing, but you would have to do something. Okay, so here, you got a 0 here. What did you do? Shifted left, right? Okay, so whenever you have a 0, you shift left. No need to add. Whenever there is a 1, you need to add and shift. So no matter what, you need to shift left by one place. However, if it's a 1, you need to add. If it's a 0, you don't need to add. Yeah? And you just accumulate that result in the product register. You guys see that? So 1, multiplicand, shift left, 0, zeros. 1, multiplicand, 0, zeros. Add all of those up, you get your answer in terms of your product register. But like we said, when we are trying to implement this in hardware, initialize product register to all zeros. By the way, there are better ways of implementing this. Right now, I'm talking about the sort of the first version of a multiplier, multiplication. Initialize it to all zeros. Keep monitoring the least significant bit of the multiplier. Oh, by the way, if I'm just looking at the least significant bit of the multiplier, I'm always going to be looking at this. So what do I need to do as far as the multiplier is concerned so that I can look at this and this and this? Shift right. You guys see that? So if I keep shifting the multiplier right, but always looking at the least significant bit of the multiplier, then I'm looking at this, 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 and this, right? So shift right for the multiplier, but shift left for the product register. You guys see that? So in our hardware, we are going to need some shift right capability. We are going to need some shift left capability. And I hope with this, you guys know where it fits in. Next, we look at the flow chart of the multiplication process. And some of these things, if you have understood that process in binary, this is going to be pretty quick. You start, the first thing that you do, as Chris said, is look at the least significant bit of the multiplier. If you look at the least significant bit of the multiplier, it could be a 0, could be a 1. If it is a 1, what do you do? So you see, if this is a 1, right? If it's a 1, that you add the multiplicand to the product register and paste the result back in the product register. We talked about that. Initialize the product register to 0. When you're doing it for the first time, it will be like multiplicand plus zeros goes into product. But when you do it for the second time, it will be accumulation. Product plus product goes into product. Sorry, product plus multiplicand goes into product. Right? Accumulation after that. So that's 1A. Add multiplicand and product. What do you do after that? You do a shift left on the multiplicand register by 1 bit. Remember, if it's a 0, you have to do that. If it's a 1, you have to do that. Right? No matter what, you have to do the shift left operation on the multiplicand. And you're doing that by 1 bit. Then you are going to do a shift right by 1 bit for the multiplier, so that you are looking at the next bit on the multiplier. Right? And then you keep continuing this 32 times in order to complete your 32-bit multiplication. You guys see that? This is straightforward. Next, I want you guys to tell me, in terms of registers, how many do I need for this, and what are their sizes? This is a 32-bit multiplication example. What are the registers I need for this? Don't think about it in terms of MIPS. Think about it in terms of the multiplication process we are looking at. Ah, nice. So 64-bit register for multiplicand. Usually this is where the most confusion is, but I'm glad to see that that was the first thing that you correctly identified. 64-bit multiplicand. Why not 32? I was multiplying 32-bit with 32-bit. So why do I need 64-bit multiplicand? I think you said it. You keep shifting left. You keep shifting left, right? So you need that place. Okay, so 64-bit register for multiplicand. What else do I need? Huh? Let's go. Go ahead. All right, 32-bit register for multiplier. What else? For the answer, right? 64-bit multiplicand, 32-bit multiplier, 64-bit multiplicand, product register. So far, we can improve it. So far, that's what we need. Let's see, no questions there. All right, let's move on. So now let's put everything into like a block diagram, which is representative of your multiplication hardware. Do you see a 32-bit multiplier? Yes. A 64-bit product register, a 64-bit multiplicand register, right? A 64-bit ALU. Why 64-bit ALU? Well, 64 bits plus 64 bits. So you're going to need a 64-bit ALU. So in terms of efficiency, in terms of the size of these registers, I hope that you guys are a little bit concerned. My multiplication was 32-bit, but I'm using a 64-bit ALU, a 64-bit multiplicand. Both of these are sort of maybe reduced, right? I can improve that. Ideally, I would have wanted to use a 32-bit multiplicand and a 32-bit ALU for this. My product, sure, that needs to be 64. So there are better ways of doing this. All right, let's come back to this. There is a control test over here. What is this guy looking at? This guy is looking at the least significant bit of your multiplier, right? So it takes in one information from the multiplier. LSB of multiplier. So the control test is a circuit that is going to observe the least significant bit of the multiplier, and it is going to send all the other signals to the other registers. For example, when do you need to shift left 1 bit for multiplicand? When do you need to add? When do you need to write the results of that addition into the product register? When do you need to do a shift right for the multiplier? All of these are related to the flowchart before. And the flowchart before is related to the multiplication operation that we talked about in binary. So how are things going to work? Well, you would initialize everything in your product register to be all 64 zeros, right? You look at the least significant bit of the multiplier. Could be a 0, could be a 1. If it is a 0, you just do shift left for this guy, and you do shift right here. You don't need to do addition, don't need to do any updating of the product register. If it's a 1, what do? You take the multiplicand, add it to the product register right now, put the result back into the product register, and then shift left. You see that? So you're continuously look, and obviously update the multiplier as well. Move it right by 1. So everybody okay with the size of the registers and sort of the purpose of the control test block there? Look at the least significant and then send the appropriate controls for all the others, all the other components. Shift and add operations being carried out. Shifting is being done by control test. Addition is being done by ALU. Questions here? All right, in a few more minutes here, let's take a look. Second version. Like I said, there are a few things that we can improve. What are we going to improve? First, observe that the multiplicand is not changing, right? A multiplicand register is not changing. All we are doing is shift left operations on that multiplicand. So if we start with multiplicand 32 bits here, and then a bunch of zeros there, for example, we are just shifting all the way over here, right? But it's not changing. It's not that it is multiplicand operand is changing. We are just shifting it left. Can we make it into 32 bits? That's the first question. And the answer is yes, of course. The next one in the second version is shift product right instead of shift multiplicand left. You are adding things to the product register. And if you are moving this guy left, and your product register is stagnant, 64 bits, right? This guy is moving left. It is the same effect as keep this as is and move this guy right, so that you move to the more significant positions on the answer. Because that's the goal, right? As you're doing that addition, you are moving to the more significant positions on the product register. So you can do that by moving left here or right here. So we are going to try to use the second scheme here, just because it will help us save some hardware, some registers. And then we will, this version will also allow for 32-bit ALU and a 32-bit multiplicand register. Let's take a look. How is this changing? Multiplicand has changed from 64 to 32 bits. Good. ALU has changed from 64 to 32 bits. Multiplier was 32 bits, is still 32 bits, no problem. But you see what has happened to the product register here. Product register is 64 bits. However, it is moving right instead of this guy moving left. And what are we doing here? Let's look at the flowchart there. Start, look at the least significant bit of the multiplier. Could be a 0, could be a 1. If it is a 0, you just shift the product register right by 1. Earlier, you were moving the multiplicand register left. Here, you are moving the product register right by 1. But if it is a 1, you see what is happening. Add the multiplicand to the left half of the product. Add the multiplicand to the left half of the product. Add here, move right. Add here, move right. Add here, move right. So you are accumulating that 64-bit result in a slightly different manner, so that you can get away with a 32-bit multiplicand. You don't need a 64-bit multiplicand right now, right? So you continuously add here, move right. Add here, move right, and so on. Only when things are 1. If things are 0, you just move product register right by 1 bit. Yeah, go ahead. Right. So the answer is only affecting these positions. So this is, say, 32 lines, right? So those are controlling the 32 bits of the 64-bit product register. How? You can say, let's take all those 32 bits, go into D flip-flops, 32 of them, and when you clock it, these 32 change, the other 32 are going to remain as is. But then you have to do a shift right by 1. So when you do that, shift right by 1, they will all move 1 bit up by 1, right? So you can actually start with, say, zeros over here, or you can have any junk there. It will just keep getting pushed out. So add multiplicand, move right. Add multiplicand, move right. Continue doing that for 32 bits. Only when they are ones, right? If they are zeros, you don't even need to do that addition. You just do the shifting. So another thing that changed over here is the control test, depending on the multiplier, least significant bit of the multiplier, it is sending a shift right signal for that product register. Earlier, that wasn't there. Right? It was just writing it. All right, let's come back here. Everything else is the same. Only two things changed. Product register moving right instead of multiplicand moving left. The other is when you do that addition, you are adding and putting that result in the left half of the product register. That's only, instead of all of the product register. All right, so this is your second version. In fact, you can do a final version, which is sort of your most improved multiplier, which is lower half of the product register was wasted space, right? So we have product register, which has two spaces here, 32 there, 32 there. We have split it in half. Maybe we can use that for the multiplicand as well. So what multiplier, right? So multiplier is consumed anyway. What does that mean? After you look at the least significant bit of the multiplier, you're shifting right. When you shift right, your multiplier bit is getting consumed, right? It's getting thrown away as you're shifting. So what can you do? You initially put the multiplier in the lower 32 bit of the product register instead of having just zeros, like or some arbitrary bits. Have the multiplier over there in this space. Have this over here, right? And then shift the product register and the multiplier to the right together. How is that going to look like? It's simply going to look like this. Multiplier register has disappeared. Multiplier register has become part of the product register itself. So what are you doing? You're looking at the least significant bit of the multiplier here. You are still doing 32-bit addition. You still have the multiplicand. You are shifting product register to the right every time by 1. And when you do that, you are throwing away the multiplier least significant bit which got consumed. No problem. Right? So this avoids even the use of the multiplier register. Yes, okay with that? So what are you going to initialize your product register as? It is going to be a bunch of 64 bits, right? 64 bits. The 32 most significant bits are 0, and the 32 least significant bits are the multiplier. Then you do that addition. Multiplicand keeps getting added to the 32 bits over here on the left. Move right. Add left, move right. You guys see that? Yeah? All right. So this is your final version of the multiplication. For when you're dealing with sign multiplication, we are going to keep track of the sign with a separate circuit. So we just convert the negative numbers to positive. We'll go through the multiplier, and then we'll have separate circuit to keep track of the sign. All right. When we come back on Monday, I'll talk about faster multiplier. Then I'll get into division operation. Shouldn't take too much time. It's going to be very similar to our multiplication, except now it's going to be subtractions, right? Instead of additions, it's going to be subtractions. And then we'll get into the IEEE standards. So my goal for Monday is to finish this and to finish the IEEE 32-bit and 64-bit standards. And we have exam 1 coming up as well. When is exam 1? You guys know? Uh, 26th. 26th? Yes, 26th. So 2 Thursdays from today. Sort of a good time to start thinking about what to do on weekends. All right, I will stop recording here, you guys. 24th? I thought it was 26th. Oh, okay, so 24th. You're right. 2 Thursdays is 20. All right, you're right. You're right. 24th. Thursday, June 24th.